Okay, we have the reactions of alkynes. So the last chapter went over the reactions of alkenes, okay? And you'll find that alkenes and alkynes have very, very similar modes of reactivity. So as long as you had a good understanding of alkenes and their reactivity, alkynes will be pretty easy to grasp, okay? So there's two types of alkenes. There's internal and terminal alkenes, or sorry, alkynes. An alkyne is internal if there's carbons on either other side, right? We have a carbon here, that's the triple bond. We have another carbon. So it's internal, right? Here, this carbon that's part of the alkyne is it's uh it's on the outside, right? It's terminal. So also make sure to draw alkynes as linear. So these triple bonds have to be flat, right? You draw a double bond like this, but you draw an alkyne like this. Okay? So alkynes are nucleophiles. They're slightly less reactive than alkenes, just because in a triple bond, the electrons are held more tightly, which makes an alkene more reactive. These are the stability trends. Vinylic means like right on the bond, right? Addition of hydrogen halides to an alkyne. Okay, so they follow Markovnikov's rule. Alkene is less reactive than the starting alkyne because C1 inductively withdraws electrons. So what's going on here? Once I add the HCl here, I have a double bond. I added H on one side and a Cl on one side, right? So what do I mean by less reactive? So this structure is less reactive than just a regular old double bond like this, right? And that's because a nucleophile is all about having extra electron density, right? This Cl is pulling electron density from the thing that's supposed to be attacking. So this thing that's supposed to be negative or electrophilic, or sorry, having a lot of electron density, nucleophilic, has now like reduced its electron density. So it's less nucleophilic, so it's less reactive. So if I were to add one equivalent of HCl, the reaction will stop at the alkyne. Um, sorry, the reaction should stop at the alkene. I don't know why I wrote alkyne. Um, HBr excess or 2-HBr, we can add it to the same position twice. HBr here, we add to opposite sides. Okay, cool. An alkyne is unsymmetrical and internal. We'll get two different products. We see here that there's no regioselectivity because this is a tertiary spot. This is a secondary spot. This is a secondary spot. So there's no regioselectivity. There's no region for which it would select. Addition of a halogen. So the first step is the halogens will add on opposite sides. If you use excess, we'll just get di, tri, quattro brominated compounds where we have these CLs add again, right? So we'll add Cl, Cl again. Addition of a water to an alkyne. Okay, so this is a little bit funkier, and I think it's important to slow down here because I think this is one of the mechanisms that's a little bit different than what we're expecting with alkenes, right? We saw how these are basically parallels of what we were expecting in alkene reactions, but this alkyne is a little bit different. So when you add water to an alkyne, you go through something called a tautomerization, um, and you're not really on the hook for this mechanism yet. Um, I guess you are to an extent, but you'll really learn more about the tautomerization mechanisms at the tail end of 109B. This is something called an alpha carbon reaction. And again, you're not there yet. So all this just to say is that this is a little bit more advanced. So let's look at what's going on here, right? Let's start here, right? H2O, H2SO4, we add an OH on one side, we add an H on the other side. This is exactly what we would expect, right? So I think it's sufficient to kind of memorize that whenever we have a double bond directly connected to an OH, it'll tautomerize to form a ketone. So all that means is we switch the double bond from this to this, okay? So we put the hydrogen here and we put the double bond here instead. And this is the mechanism of exactly what's happening. There's two types of ways to catalyze it. There's acid catalyzed and there's base catalyzed. Base isn't covered here, but this is what's going on. Okay, so these lone pairs are coming down, and this is grabbing a hydrogen, kicking this off. So now we have a double bond form here. We do protonate this H, and we end with this. Okay, and in reverse, this is what's going on. Okay, internal alkenes don't require a catalyst. Cool. Okay. Non-symmetric, we don't have any regioselectivity, so we just form both products. Okay. Hydroboration oxidation of an alkyne. So again, the first step is what you would expect. We add H and BH2, except we have an extra double bond. Hydroboration oxidation, we replace the BH2 with an OH, exactly what you'd expect. And the one thing that we weren't really expecting, but now we know how to look out for, when we have a double bond, line, OH, it forms a ketone. Cool. And this is the base catalyzed version of the tautomerization. Under acidic conditions, you do not generate a strong base. Under basic conditions, you do not generate a strong acid. So it's just saying, like, like if you're asked to draw out this mechanism, if it's base catalyzed, you have minuses, you have neutral structures. You never have a plus on any of these. For acids, you have a plus, you never have a minus, you can have neutral. Okay, cool. Reduction of alkynes, hydrogenation. So H2 palladium on carbon will actually end up reducing this all the way. This is a syn addition, so we're adding these hydrogens on both sides, okay? So there are examples of reagents that's, first of all, do slightly different things. Lindlar's catalyst is something called a poison catalyst, so it stops at the alkene. So it will reduce a triple bond to a double bond, but it will not reduce a double bond. NaLi, NH3L, minus 78 degrees Celsius. Whenever you see minus 78 degrees Celsius, it's kind of a clue that you're stopping one away from what could happen, right? A triple bond could go to a single bond, but since I'm saying minus 78, I'm saying this is a mild condition. So I'm only stopping the double bond. And this produces trans or the E alkene. So these lines are on opposite sides because I add an H here and I add an H here. Here I add the H's on both sides. Cool. Alkyne acidity. So we kind of talked about these earlier. But there's a lot of stuff that you can do with an sp carbon, okay? We do a lot of synthesis with acetylide ions. So right off the bat, OH is not strong enough to deprotonate an alkyne because the pKa of this is 25, the pKa of this is 16, so it'll favor this side as opposed to this side. So we use this thing called NH2 minus. Um, it's an amide ion. Oftentimes you'll see it as NaNH2. Sometimes you might even see NaH, sodium hydride. They're all the same thing, okay? So what's going to happen is there's a carbon here and a hydrogen here, right? So I'm going to take that hydrogen off, and now I have a negative, okay? So this acetylide ion is a really good nucleophile. Carbanions are really good nucleophiles. So we can attach at this position, kick off this Br because this is a slightly electrophilic position, right? Because polar covalent bond, this Br is pulling electron density. This is a partially positive spot. It's kind of not a great electrophile, but this is a really good nucleophile. So as long as we have one that's really good, it'll happen. We attach here, we kick this up. This is flat because a triple bond is flat. Awesome. Multi-step synthesis. We'll cover that a little bit later. I guess I mean I can just, say that like the whole point of organic chemistry is to synthesize molecules, right? So a lot of the questions you're going to be asked, a lot of the challenging questions, but a lot of the, the best, most rewarding questions for like learning are going from one structure to another structure. And we have something called a retrosynthetic analysis, which is kind of just like working back. So we know the starting, we know the ending. So maybe we don't know exactly how to get there right away, but it's like, oh, like I know I have this. What's the previous step to this? What's the previous step to that? And you're kind of working backwards, like because you know the answer, so you're working backwards to try to figure out what the start was. Okay, cool. That wraps it up for alkyne reactions.